Hello again, and welcome. However your day has unfolded, whether it's stretched long and heavy or slipped by in a blur, it's over now. This is your moment to let go. Let your breath deepen. Let the weight fall from your shoulders. Let the rhythm of calm take over, steady and slow. You don't need to solve, plan, or even stay awake. All you need is to listen. Tonight, we're not drifting among stars. We're moving into the heart of the unknown, toward the most silent, most powerful anchors of the cosmos, supermassive black holes. They aren't monsters waiting in the dark. They're mysteries, older than galaxies, larger than comprehension, shaping the universe in ways we still don't fully understand. Across the chapters ahead, you'll hear 100 truths about these giants. Facts that are both grounding and strange, humbling and infinite. Some will surprise you, others may comfort you. Each will guide you deeper into rest. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or press the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world, like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. In the universe, there are black holes small enough to be born from the death of a single massive star. When such a star exhausts its fuel, its core collapses and gravity crushes it into a compact remnant only a few dozen kilometers across. These are stellar mass black holes, measured in units of a few times the mass of the Sun. They are fierce but modest, scattered like sparks across the galaxy. Yet beside them, another category exists, so vast that even the word enormous feels thin. These are the supermassive black holes, the silent engines at the centers of galaxies, each one containing millions to billions of solar masses within a region no larger than a solar system. Where stellar black holes are embers, supermassive black holes are mountains of shadow. A stellar black hole may be 10 times the mass of the Sun, but the black hole at the core of our Milky Way, Sagittarius A*, weighs over 4 million times as much. And even that is small compared to the true giants. Ton 618, one of the largest known, tips the scales at more than 60 billion solar masses. Imagine the weight of 60 billion stars, each the size of the Sun, pressed together into a point of infinite density. Its event horizon alone would span more than 1,000 times the distance from the Earth to the Sun. In sheer scale, these objects defy comparison. And yet they are real, measurable, present at the hearts of galaxies that light the night sky. Astronomers believe that nearly every large galaxy, from spirals like our own to massive ellipticals, shelters a supermassive black hole at its center. They are not rare accidents. They are fundamental, woven into the architecture of the cosmos. Our telescopes reveal stars whipping around invisible points, their orbits bent by gravity far greater than any cluster of stars could provide. In these movements lies proof that something massive and unseen exerts its pull. The galaxy you live in is not held together by starlight alone, but by the shadowed grip of a black hole resting silently at its core. The contrast between the small and the immense is staggering. A stellar black hole could swallow a mountain, yet the largest supermassive black holes could swallow entire solar systems whole. Their masses range across a spectrum so wide it stretches imagination. Some measure a few million solar masses, modest in cosmic terms, while others exceed tens of billions, becoming gravitational monarchs of their regions. To fall toward one is to cross a gulf of scale so profound that language itself trembles to describe it. We can say billions of suns. But what does that mean when one sun already feels infinite? Despite their power, these black holes do not always announce themselves. Many lie quiet, hidden in the darkness, their presence betrayed only by the stars orbiting nearby. Others flare with radiant violence when gas and dust spiral inward, heating to millions of degrees in bright accretion disks that blaze across the universe. In their active state, they can outshine every star in their galaxy combined, becoming quasars, beacons visible billions of light years away. But whether silent or blazing, they remain the same. Regions of gravity so deep that not even light can escape. It is humbling to realize that these monsters of mass are not the exceptions of the universe, but its rule. Wherever you look, at Andromeda, at the great elliptical galaxies in Virgo, at the faint smudges of light captured by Hubble in the farthest reaches, there at the center lies a black hole. Galaxies and black holes are not separate stories. They are chapters of the same tale. The stars orbit, the arms twist, the clusters drift, but at the heart of it all, a black hole waits, anchoring the motion, invisible but indispensable. This is the weight of darkness, a scale beyond stars, a presence older than memory, a silent gravity that sculpts the cosmos. To understand galaxies, you must understand their cores. And at those cores, always, is a black hole vast enough to command millions or billions of suns. When you look up at the sky, when you trace the pale band of the Milky Way, you are not just looking at stars. You are looking at the work of a hidden architect, a darkness so massive it shapes the light itself. Galaxies may look like quiet swirls of stars, but hidden at their centers, supermassive black holes act as regulators, engines that shape the fate of entire systems. Their influence is not confined to the region close to the event horizon. Gravity, energy, and motion ripple outward, guiding the rhythm of star formation, the distribution of matter, and the very structure of galaxies themselves. What might appear from a distance as serene arms of starlight is, in truth, a delicately balanced ecosystem, tuned in part by an invisible core. When gas and dust fall toward a black hole, they rarely vanish silently. Matter piles into accretion disks that spin and heat, glowing so fiercely they can outshine all the stars around them. In this act of feeding, black holes unleash winds and jets that blast outward into their galaxies. These outflows sweep across interstellar space, pushing gas into motion, scattering clouds, and in some cases preventing those clouds from collapsing into new stars. Paradoxically, by consuming matter, black holes can halt the birth of suns. Their hunger sculpts the pace at which galaxies grow, deciding whether they bloom with stellar nurseries or lie quiescent, dim, and quiet. Astronomers call this regulation feedback, though the word feels small compared to the scale of its effect. Imagine a galactic core erupting in radiation 1,000 times brighter than the Milky Way. The light and heat pour outward, heating cold hydrogen, dispersing the raw material of future stars. Too much feedback, and a galaxy starves itself. Too little, and it collapses under uncontrolled starbursts. The black hole becomes not a destroyer, but a balancer, an unseen hand that steadies the galaxy's growth. These engines also shape structure more directly. The jets launched from the poles of black holes can span hundreds of thousands of light years, carving tunnels through intergalactic space. They stretch beyond the host galaxy itself, seeding the cosmos with magnetic fields and heavy elements. Over time, such activity defines the look and fate of galaxies. Elliptical galaxies often house the most massive black holes, their shapes sculpted by ancient outflows and mergers. Spirals, like the Milky Way, carry more modest black holes, though still millions of solar masses in scale, steady hearts around which arms of stars continue to wind. We often picture galaxies as independent islands of light, but in reality, they are bound by this constant push and pull between their stars and their central black holes. A galaxy is both nurtured and restrained by its core. Without supermassive black holes, star formation might rage unchecked, burning through gas too quickly, leaving galaxies barren long before their time. With them, the tempo slows, stretching creation across billions of years, giving space for complexity to emerge, for life to one day appear under calmer skies. The most astonishing truth is that this grand orchestration is performed by something invisible. A black hole cannot be seen directly. Its gravity is so strong that even light is trapped. Yet its influence writes itself across galaxies, from the distribution of stars to the silence of spaces where no new suns ignite. What you see when you look at a galaxy through a telescope is not just stars glowing. You are seeing the shape of darkness, sculpted by the quiet engines hidden within. A black hole may seem like the ultimate end, but at the galactic scale it is also a beginning, an architect of balance and form. Their presence reminds us that the universe is not built only of light, but of forces that hide behind silence, guiding creation with a power we cannot touch or see. These invisible engines hum at the hearts of galaxies, regulating, feeding, and shaping, writing the story of the cosmos in shadows. The event horizon is not a surface you could touch, nor a wall that could stop you. It has no substance, no texture, no shimmer. It is only a boundary drawn by gravity itself, a line in space-time beyond which escape becomes impossible. Light, the fastest thing in the universe, cannot outrun it. Once light falls past this threshold, its path curves inward forever, swallowed into the dark. For anything that drifts too close, the event horizon marks the point of no return. Einstein's theory of general relativity predicted this strange frontier. Space and time are not fixed, but flexible, bending under the influence of mass. A black hole bends them so severely that at a certain distance, all possible paths curve inward. If you were to hover just outside this boundary, you might still shine a flashlight outward and see the beam drift into the void at an angle. But cross a little farther in, and even the beam pointed directly away would curve back, unable to resist. The horizon does not pull you with force, it traps you with geometry. Space itself tilts so steeply downward that every path forward leads only deeper inside. From the outside, the horizon appears like a perfect sphere of shadow, the edge where light vanishes. To an observer watching from afar, anything that falls toward it seems to slow down, moving more sluggishly with each passing moment. Time itself stretches as gravity grows stronger, and the falling object appears to freeze at the edge, fading away as if absorbed by the surface of night. In truth, the object crosses easily in its own frame of reference, slipping inward without pause. But for distant eyes, the horizon becomes a veil across which nothing can be seen. This stretching of time near the horizon is not an illusion. It is real, a consequence of relativity. A clock carried close to the boundary would tick more slowly than one held far away. To the traveler nearing the edge, seconds would pass normally, but for those left behind, those seconds would stretch into minutes, then hours, then eternity. If you tried to watch someone fall, you would never see them cross. They would remain, suspended at the threshold, dimming into darkness until their image faded completely. In that way, the event horizon is both an end and a curtain. It is tempting to think of the horizon as the black hole itself, but the reality is stranger. The horizon is only the limit, the border drawn by gravity's rule. Inside lies the singularity, a point where density becomes infinite and our physics falters. The horizon shields this heart, not by choice but by necessity. It keeps the singularity hidden forever, an unreachable secret. We can describe its effects, measure its influence, even photograph the glowing rings of matter around it, but the singularity itself remains beyond reach. The horizon ensures that mystery is preserved, and yet the horizon is not fixed. Its size depends on the mass of the black hole. For a black hole like Sagittarius A times at the center of the Milky Way, the horizon stretches across a region larger than Mercury's orbit around the Sun. For monsters like Ton 618, it would dwarf the solar system entirely. Every black hole carries its own horizon, a shadow whose radius grows with its weight. Though invisible, This boundary becomes one of the most important features in the cosmos, marking where the universe turns inward on itself. The event horizon is not merely a boundary in space, it is a boundary in knowledge. Beyond it, information cannot return. Whatever falls inside is sealed away, cut off from the universe, perhaps lost forever. When you gaze into the blackness at the center of a galaxy, you are looking not just at absence, but at a threshold where the laws of physics permit no return. It is a frontier not of exploration, but of endings. And yet, in its silence, the horizon is beautiful. A perfect, smooth limit, drawn by gravity itself, holding within it the greatest secrets of the cosmos. The singularity is the heart of the black hole, but the word heart feels too gentle for what it means. It is not a place, not even a thing, but a collapse of all matter and space into a point of infinite density. Imagine every atom crushed beyond recognition, every particle forced together without limit, until even the laws of physics can no longer describe what remains. Here, the equations break. Gravity grows infinite, time and space fold inward, and the very language of science fails. Einstein's theory of general relativity guides us faithfully until this point. It predicts that once matter falls beyond the event horizon, there is no stopping the descent. The inward curve steepens until nothing can resist, until all paths lead to the same final destination, the singularity. In this picture, space-time itself collapses, dragging matter into a region of zero volume and infinite curvature. Yet the idea of infinity signals not understanding, but the limits of our understanding. Where we write infinite, we admit that our current physics cannot continue the story. Some physicists imagine the singularity as a place where all known forces of nature merge into one. At scales so small and energies so high, quantum mechanics and relativity can no longer be separated, yet no complete theory exists to unify them. String theory, loop quantum gravity, and other frameworks reach toward this frontier, but none has yet bridged the gap. The singularity is not just a mystery of matter, but a frontier of knowledge. What lies there might reveal the deepest truths about the universe, but no signal can escape to tell us. To those falling inward, the singularity is inevitable. A spacecraft that somehow crossed the event horizon would have no path to steer away. Time itself becomes a funnel, drawing everything to the same point. Unlike the event horizon, which only appears static from the outside, the singularity is final, even from within. No traveler, no particle, no fragment of information could continue beyond it. To approach it is to approach the end of history, the place where the concept of after dissolves. And yet, even this may not be the final word. Some theories suggest the singularity could be avoided, that quantum effects might smear out the point of infinite density into something finite, a core where physics still makes sense. Others wonder whether the singularity could be a doorway, a bridge to another universe, or the seed of a new Big Bang. These ideas are speculative, but they arise from the recognition that infinity is not an answer. It is a question mark, pointing toward a deeper truth. From the outside, we may never know. The horizon keeps it secret. What happens beyond remains hidden, locked away in darkness. We can circle the edges, measure the pull, watch the jets and flares of matter being devoured, but the singularity itself remains untouchable. It is the silent center of the black hole, a mystery wrapped in mathematics, a riddle whose answer may hold the key to the universe itself. The singularity is not only a collapse of matter, it is a collapse of certainty. It reminds us that the universe contains places where our knowledge falters, where even the most brilliant theories bend and break. To face the singularity is to face the unknown in its purest form, and in that unknown there is awe as well as fear. It is a place where imagination stretches as much as physics, where the human mind confronts the infinite and admits its limits. What lies beyond the singularity is not something we can measure or see. It is something we can only wonder about, a silence at the center of darkness. Yet in that silence lives possibility, the promise that one day our understanding may grow enough to peer into the abyss and find not an end, but a new beginning. Black holes cannot be seen directly, yet their presence is written into the cosmos in ways too clear to ignore. Astronomers hunt them not with sight, but with traces, with the shadows they cast on their surroundings, with the motion of stars and the trembling of light. To measure the invisible requires patience, creativity, and faith in physics, for what we are looking for cannot send us a message of its own. It must be inferred from the way the universe bends around it. One of the clearest signs comes from watching stars near galactic centers. Around Sagittarius A*, our galaxy's black hole, astronomers have tracked stars tracing dizzying ellipses, racing around an unseen point, with speeds so great that nothing less than millions of solar masses could hold them. These stars do not orbit empty space. They orbit a compact source of gravity, smaller than the orbit of Mercury, yet heavier than 4 million suns. By tracing their paths over decades, astronomers have painted the signature of a black hole without ever glimpsing it directly. The motion of these stars is like handwriting on invisible paper, spelling out the weight of the unseen. Other clues come from matter falling inward. Gas and dust caught in the gravity well form accretion disks that spin and grind, heating to millions of degrees as friction tears them apart. The result is radiation across the spectrum, but most vividly in X-rays. When telescopes tuned to high energies look into the sky, they find flares bursting near black holes, sudden outpourings of light from matter just before it vanishes. These signals are brief, violent, and revealing. They tell us not only that a black hole is feeding, but how it consumes, how close matter can orbit before the abyss claims it. The X-rays are the last cries of particles before silence. Sometimes the feeding becomes spectacular. Jets of plasma erupt from the poles of black holes, streaming outward at nearly the speed of light. Though the jets themselves are visible, their presence implies the disk that fuels them. What we see is not the black hole, but the drama of matter under its spell. The brighter the flares, the more ferocious the accretion. The quieter the region, the hungrier the shadow. In this way, astronomers read activity as if listening to a cosmic heartbeat, diagnosing the invisible through the rhythm of light. Even more subtle are the distortions of space itself. Black holes bend the paths of photons passing nearby, acting as gravitational lenses. A star hidden behind a black hole may appear doubled or stretched into rings, its light curved around the unseen mass. To witness this effect is to see gravity at its purest, space warped into a lens by nothing more than presence. By measuring these distortions, astronomers calculate the mass of what cannot be seen. It is a way of turning darkness into data, a method of weighing shadows by the way they bend light. Piece by piece, the invisible becomes measurable. The orbits of stars, the glow of accretion disks, the outbursts of X-rays, the curves of lensed light, all converge on the same truth. Something immense, compact, and inescapable exists at the centers of galaxies and scattered across the universe. Though no light escapes them, they cannot hide, for the universe itself betrays their presence. To measure a black hole is to listen to whispers around silence, to read the margins of a story whose center will never be revealed. It is an act of faith and precision, a reminder that even the deepest shadows leave their marks on the cosmos. At the center of the Milky Way, hidden behind clouds of gas and the glare of countless stars, lies Sagittarius A*. It is our galaxy's black hole, a dark anchor around which everything orbits, though for most of human history we had no idea it was there. Through early telescopes, the core of the galaxy looked only like a crowded smear of starlight, impossibly dense and dazzling. Only with the advance of radio astronomy, infrared detectors, and decades of patient observation did we begin to see what was truly hidden within that glow. A point of gravity 4 million times heavier than the sun, pulling silently on everything around it. Its discovery was not a sudden revelation but a slow unfolding, like a photograph developing in darkroom chemicals. In the 1,970 seconds, astronomers pointed radio telescopes at the center of the galaxy and detected a compact source unlike anything else nearby. They called it Sagittarius A*, an unassuming name for something so profound. Over time, with sharper instruments and careful measurements, they began to trace the paths of individual stars close to the galactic core. These stars, some of them enormous in their own right, were whipping around an invisible mass at speeds of thousands of kilometers per second, completing orbits in just a handful of years. No cluster of stars, no hidden cloud of gas, no ordinary explanation could account for such a gravitational pull. The simplest and only possible answer was a black hole. Sagittarius A* is not the largest supermassive black hole we know of, not even close, but its nearness makes it extraordinary. It is about 26,000 light-years away, close enough that our instruments can pick out the motion of stars around it, like fireflies circling a lantern. This proximity has turned Sagittarius A* into a natural laboratory, the best place to study black holes up close without leaving our galaxy. The 2020 Nobel Prize in Physics was awarded to scientists who mapped these stellar orbits in exquisite detail, proving beyond doubt that a black hole rests at the Milky Way's core. What once was theory became certainty, written in the dance of stars around an unseen center. Unlike some black holes in the distant universe that roar with luminous accretion disks and jets, Sagittarius A* is relatively quiet. It feeds only sparingly, nibbling at wisps of gas rather than feasting on torrents of matter. Occasionally it flares, sending a brief flash of X-rays across space, but for the most part it waits in silence, almost dormant. Its calmness has spared the Milky Way from violent outbursts that might have stripped away gas and stunted the galaxy's growth. Instead, our black hole has watched quietly while stars have formed, planets have gathered, and life has had time to emerge on a small blue world in one of the spiral arms. And yet, even in its quiet state, Sagittarius A* shapes the entire galaxy. The Sun, Earth, and every star you see at night orbits the Milky Way's center, bound by the gravity of its combined mass, but anchored by the presence of the black hole at its heart. Without it, the structure of the galaxy would be different, its history rewritten. This unseen presence holds the spiral together, a reminder that what we cannot see can still determine everything. In 2022, the Event Horizon Telescope collaboration revealed the first image of Sagittarius A*, a glowing ring of hot plasma encircling a dark shadow, the silhouette of the horizon itself. The picture was blurry, imperfect, more suggestion than portrait, but it carried the weight of confirmation. For the first time, humanity could look at the very edge of our galaxy's black hole, a shape carved not in light, but in its absence. That image is more than science. It is a reminder of our place, orbiting within a galaxy whose core is ruled by something we will never touch yet can finally begin to glimpse. Sagittarius A* is not just a black hole. It is the center of our home galaxy, the anchor of our spiral, the silent force around which every star, planet, and cloud of gas revolves. It is the dark heart of the Milky Way, patient and enduring, a mystery that has defined us long before we knew it existed, and will continue to define us long after we are gone. When we imagine a black hole, even a stellar one feels incomprehensible. A collapsed star heavier than our sun compressed into a region the size of a city. Yet there are black holes so vast, so staggeringly heavy, that even comparison feels fragile. These are the true giants of the universe, supermassive black holes, not of millions, but tens of billions of solar masses. They live at the centers of galaxies larger than comprehension, and they reign over their cosmic neighborhoods with a gravity that dwarfs anything else we know. Among them is TON 618, one of the most massive black holes ever discovered. Astronomers studying a distant quasar, the blazing beacon of a feeding black hole, realized that the source could only be explained by a monster with more than 60 billion times the mass of the Sun, 60 billion suns, compacted into a single abyss. Its event horizon would stretch beyond the orbit of Neptune if it sat at the center of our solar system, swallowing not just the planets but the emptiness between them. Ton 618 is so far away that its light began its journey toward us more than 10 billion years ago, meaning we see it as it was when the universe itself was young. And even then, it was already enormous, a puzzle that forces us to wonder how such a giant grew so quickly. Closer to home, though still unimaginably distant, lies Holmberg 15 Amperes asterisk, the central black hole of a massive galaxy in the Abell 85 cluster. This titan is estimated at around 40 billion solar masses, making it one of the heaviest black holes measured in the nearby universe. To speak of billions of suns in one place is to step outside language, but imagine the Milky Way with its 4 million solar mass black hole, and then multiply that mass 10,000 times over. Holmberg 15 Amperes times is not merely a central object, it is the defining core of its galaxy, a gravitational monarch dictating the fate of trillions of stars that circle around it. These giants are not common. Most galaxies, even large ones, contain black holes of a few million to a few billion solar masses, but in certain environments, rich clusters of galaxies, regions where mergers are frequent and fuel abundant, black holes can grow beyond all ordinary bounds. They do so by devouring matter in torrents, by colliding and merging with other black holes, by feeding on the dense flows of gas that once filled the early cosmos. Each act of growth leaves behind a deeper well, a larger shadow, a gravity that stretches farther into the galactic core. Over billions of years, a rare few reach the scale of TON 618 or Holmberg 15 Amperes asterisk, cosmic outliers whose size alone challenges our models of growth and time. The scale of these entities bends not just physics, but imagination. Their event horizons span light days across, meaning that a beam of light would take days, even weeks, to cross from one side of the shadow to the other. If one were placed in the heart of our solar system, every planet, every moon, every trace of orbiting debris would be consumed, not because they would instantly fall inside, but because the horizon itself would engulf the whole architecture of our system. To stand in such a place, were it possible, would be to stand on the edge of infinity stretched wider than 1,000 lifetimes. And yet, despite their enormity, these giants are invisible to the eye. We know them only through the brightness of their quasars, the orbits of stars in their neighborhoods, and the subtle ways their gravity shapes galaxies around them. They do not shine themselves, but they ignite their surroundings, turning falling matter into light so powerful it can be seen across the observable universe. Ton 618 blazes as one of the brightest quasars ever found, its energy spilling outward from a maelstrom we can never touch. In these giants lies a contradiction. They are silent, devouring, invisible, and yet they become the brightest objects in the sky. They are singularities, infinite in density, yet their shadows stretch wider than solar systems. They are rare, but their existence tells us the universe allows for growth without obvious limit, a reminder that time and gravity together can build monsters that defy our sense of scale. To think of them is to feel the weight of the cosmos pressing in. Our galaxy's central black hole feels small beside them, just 4 million suns against tens of billions. And yet, all of them, from the modest to the monstrous, to share the same truth. They are the final shape of gravity left to run wild, the giants of the universe, whose very existence teaches us how small even galaxies can seem in comparison. When we look at the largest black holes, the natural question rises almost immediately. How could something so vast ever come to be? The answer is that we don't fully know. But astronomers have pieced together several theories, each offering a path from the ordinary universe to the extraordinary gravity of a supermassive black hole. None excludes the others, and it may be that all of them have played a role, depending on when and where in the cosmos a black hole was born. One route begins with stars, the very first stars to ever shine. In the earliest universe, when matter was still pure hydrogen and helium, stars could grow to sizes far beyond those we see today, hundreds of times the mass of the sun. These titans lived brief, violent lives, burning fast and bright, before collapsing under their own weight. When they did, their cores collapsed into black holes, far larger than the remnants left behind by ordinary stars. Over cosmic time, these seed black holes could feed, merging with others and drawing in gas until they grew into the giants we see at the hearts of galaxies. In this picture, the supermassive black holes are descendants of ancient stellar deaths, stretched across billions of years of patient growth. Another possibility bypasses stars altogether. Instead of forming from the collapse of a single massive star, some black holes may have arisen directly from the collapse of primordial gas clouds in the early universe. Picture a vast, dense cloud of hydrogen, unbroken by the cycles of star birth and death, collapsing straight into a black hole before stars ever had the chance to ignite. This direct collapse scenario produces heavier seeds from the start, hundreds of thousands of solar masses in one instant. Such black holes could explain why we see quasars already blazing less than 1 billion years after the Big Bang. There simply may not have been enough time for a tiny stellar mass seed to grow so quickly unless some were born already enormous. Growth itself is another answer, one that doesn't require anything exotic, only time and fuel. Once a black hole exists, even if it is modest in size, it can feed. Gas drifting toward a galactic center spirals inward, heating as it falls, shining in X-rays before disappearing across the horizon. Whole stars can be shredded if they wander too close, their fragments joining the feast. Black holes merge with other black holes when galaxies collide, each merger doubling or more their mass. Over billions of years, this steady accumulation builds monsters from humble beginnings. It is not the suddenness of their birth, but the persistence of their appetite that creates the largest giants. Mergers play a particularly important role in the largest known cases. Galaxies do not live in isolation. They drift together in clusters, collide, and fold into one another. When this happens, their central black holes eventually find each other, spiraling inward over millions of years until they combine in a single, larger object. Each collision sends ripples through space-time, gravitational waves, but leaves behind a heavier black hole. Repeat this across cosmic time, and you can imagine how a black hole could grow not just by eating stars and gas, but by absorbing its peers. The cores of galaxies become melting pots, and what emerges is something larger than either galaxy could have produced alone. What we do know is that supermassive black holes were already present when the universe was young. The quasars we see at great distances, their light stretched by billions of years of travel, reveal black holes of 1 billion solar masses shining less than 1 billion years after the Big Bang. Somehow, they grew quickly, much faster than our simple models predict. This is the puzzle that keeps astronomers searching for answers, for the balance between stellar collapse, direct collapse, and the relentless patience of mergers. Each theory explains part of the story, but together they remind us that the universe is inventive, willing to build its giants by any means it can. The mystery of their origins is still open, but whether they came from the deaths of the first stars, from the collapse of ancient clouds, or from the slow choreography of galaxies colliding, one truth remains. Black holes are not just the end of things, they are also beginnings of galaxies, of cosmic structures, of the stories we are still trying to understand. When matter drifts too close to a black hole, it does not fall straight inward like a stone dropped in a well. Instead, it spirals, caught by its own angular momentum, circling again and again until friction and gravity drag it closer to the edge. This spiraling creates one of the most spectacular structures in the universe, the accretion disk. Though the black hole itself emits no light, the disk around it blazes with energy, becoming one of the brightest objects in the cosmos. An accretion disk forms from gas, dust, and even the remnants of stars that wander near enough to be captured. These materials flatten into a disk, orbiting at incredible speeds, each particle tugged and twisted by gravity while colliding with others. Friction heats the disk to extreme temperatures, millions of degrees in its inner regions, hot enough to glow across the spectrum. To distant telescopes, this radiation reveals itself as ultraviolet light, X-rays, and visible brilliance, a halo of fire around the black hole's shadow. The black hole may be dark, but the process of feeding transforms its surroundings into a cosmic furnace. Closer to the event horizon, the energy intensifies. Matter there moves at a significant fraction of the speed of light, crashing and compressing in ways that stretch atoms themselves. The heating is so fierce that electrons are stripped from nuclei, leaving behind plasma, a sea of charged particles spiraling in magnetic fields. This plasma radiates in pulses and flares, broadcasting the violence of its descent. The disk is not steady. It flickers and brightens, sometimes flaring unpredictably as clumps of matter plunge inward, releasing their energy in sudden bursts before vanishing forever. The inner edge of the accretion disk is defined by the innermost stable orbit, the last circle where matter can revolve without falling directly into the abyss. Beyond this point, the spiral becomes irreversible. Observing this edge provides one of the most direct tests of general relativity, because the exact location of the orbit depends on the black hole's mass and spin. By studying the light from accretion disks, astronomers can measure not only how massive a black hole is, but also how fast it rotates. The radiation carries a fingerprint of the black hole's nature, encoded in the way light shifts and bends as it fights to escape the grip of gravity. Accretion disks are also engines of growth. They are the channels through which black holes gain their mass, steadily feeding on the matter delivered by galaxies. But they are not only consumers, they are creators of light, sculptors of their environment. The radiation they emit heats surrounding gas, influencing whether new stars can form in nearby regions. Jets launched from the disk's magnetic fields can expel matter thousands of light years outward, shaping galaxies far beyond the black hole's immediate reach. In this way, the accretion disk becomes more than a sign of feeding. It becomes a regulator of cosmic ecosystems, connecting the hidden darkness of the black hole to the visible brilliance of galaxies. What makes accretion disks extraordinary is that they transform destruction into beauty. Matter falling to its doom ignites one final time, releasing more energy in its last moments than it could have produced across billions of years as a star. A single black hole, though invisible, can shine brighter than entire galaxies because of the disk that swirls around it. It is an irony written into the cosmos. The darkest objects are surrounded by the brightest fires. To watch an accretion disk through a telescope is to glimpse the process of consumption elevated into spectacle. What we see is not the black hole itself, but the struggle of matter at its threshold, blazing as it loses its battle with gravity. These disks are the great lanterns of the universe, burning not with creation, but with surrender, illuminating the skies with the light of things in their final moments. In their glow, the invisible becomes visible, and the silence of the black hole is framed by the brilliance of cosmic fire. In the vast darkness of the cosmos, some of the brightest lights are born not from stars, but from their destruction. Quasars are the beacons of the universe, powered by supermassive black holes, feeding with an intensity so great that they outshine entire galaxies. They are paradoxes of light and shadow, the darkest objects known to science, producing the most radiant displays ever seen. A quasar begins with an accretion disk, matter spiraling into the maw of a black hole. But in the most extreme cases, when the black hole is supplied with abundant fuel, dense streams of gas, shredded stars, or the debris of galactic collisions, the disk becomes almost unbearably bright. Friction and gravity heat the matter to such extremes that it radiates across the spectrum, pouring out energy not just in X-rays but in visible light, ultraviolet, radio waves, and more. The luminosity is staggering. A single quasar can shine with the power of 1 trillion suns, bright enough to be seen from billions of light years away, its glow crossing the history of the universe to reach our telescopes. From Earth, the discovery of quasars was at first confusing. In the 1,960 seconds, radio telescopes detected strange signals coming from what appeared to be star-like points of light. When their spectra were analyzed, the features were shifted to red by enormous amounts, revealing that these sources were unimaginably distant. Yet, despite their remoteness, they blazed with an intensity greater than whole galaxies. The only possible explanation was that something compact and powerful was pouring out energy on a scale never before imagined. The term quasar, short for quasi-stellar radio source, was born, though the mystery of their nature took years to solve. Today we understand that they are the throats of feeding black holes, their light the last scream of matter before disappearance. Quasars are not steady candles but dynamic flames. Their brightness can flicker over days or weeks as clouds of gas surge inward, flare, and vanish. This variability tells astronomers that the light comes from a region no larger than a solar system, despite the output rivaling galaxies tens of thousands of light years across. In some quasars, relativistic jets erupt from the black hole's poles, twin beams of plasma accelerated nearly to the speed of light. These jets extend for millions of light years, drilling through intergalactic space, visible in radio and X-ray light as cosmic lighthouses aimed across the void. What makes quasars so extraordinary is not only their brightness, but their age. Many of the quasars we see lie at enormous distances, meaning their light began traveling to us when the universe was still in its youth. Some shone less than 1 billion years after the Big Bang, already powered by black holes of 1 billion solar masses. Their existence challenges us, forcing new questions about how black holes grew so quickly and how galaxies and black holes have been intertwined since the beginning. They are not only beacons of light, but also beacons of history, carrying with them messages from the earliest epochs of cosmic time. And though they are rare today, our own Milky Way's black hole lies quiet, faint, compared to these blazing giants. In the early universe, quasars were common, dotting the skies like distant lanterns. Galaxies then were young, rich with gas, and collisions frequent, providing black holes with the fuel they needed to blaze at full power. Over billions of years, as galaxies matured and gas supplies dwindled, most black holes grew quieter, settling into the shadows, but their past brilliance is still visible, the fossil light of quasars crossing space and time to reach us. Quasars remind us of the duality at the heart of black holes. They are objects of silence and secrecy, hiding all that falls within, and yet in the act of feeding they produce some of the loudest, brightest signals the universe has ever known. They are contradictions made real, darkness cloaked in fire, a beacon not of safety, but of cosmic hunger. To see one is to glimpse a black hole at its most alive, consuming the universe and yet illuminating it at the same time. At the edge of a black hole, time itself begins to falter. The ticking of clocks, so steady in our daily lives, bends and stretches under the weight of gravity until seconds no longer mean the same thing. What feels like an ordinary moment to someone falling inward becomes, to a distant observer, an eternity. This is the strange gift of relativity, one of Einstein's deepest insights. Time is not absolute. It can flow differently depending on where you stand, and nowhere is that difference more dramatic than near the horizon of a black hole. Imagine 2 clocks, one kept far from the black hole and another carried downward, closer and closer to the event horizon. From the perspective of the distant clock, the one descending slows. Its ticks stretch farther apart, its rhythm lengthening as gravity deepens. What should have been a second appears to last 2, then 5, then an endless pause. The closer the clock approaches the horizon, the more it lags until, at the boundary itself, it seems to stop altogether. To the outside universe, nothing ever truly falls in. It only appears frozen at the edge, fading from sight as its light is stretched thinner and redder until it disappears. This stretching of time is known as time dilation, and it is not an illusion. For the person carrying the descending clock, nothing unusual seems to happen. Their seconds pass normally, their heartbeat keeps its pace, their thoughts flow without delay. To them, the fall is swift. They cross the horizon in finite time, drawn inward without resistance. But to those left behind, watching from afar, that same moment stretches into forever. It is a contradiction only in appearance. Relativity allows both experiences to be true, each consistent within its own frame of reference. The slowing of clocks is only part of the story. Light itself is also altered by the immense pull of gravity, a phenomenon called gravitational redshift. Photons climbing away from the black hole lose energy, their wavelengths stretched. What might have begun as visible light becomes infrared, then radio, fading beyond what eyes or even instruments can detect. To an observer, an object falling into a black hole grows dim, not because it has vanished suddenly, but because its light has been shifted beyond perception. The universe erases it slowly, gently, by pulling its glow into wavelengths too long to see. The event horizon marks the ultimate point of no return, and relativity dictates that once past it, even light cannot escape. But outside that line, all of these effects begin to show themselves. Time bends. Space curves. Light struggles uphill against the gravity well, growing fainter and redder with each attempt. For distant astronomers, the horizon appears not as a sharp boundary, but as a veil across which information slows and fades, a curtain where time itself is stretched so thin that it nearly stops. This strange relationship between time and gravity is not confined to theory. We experience it, faintly, here on Earth. At sea level, clocks tick fractionally slower than those on mountaintops, simply because gravity is slightly stronger closer to Earth's center. Astronauts in orbit age microseconds faster than those on the ground. The effect is so precise that our GPS satellites must account for both the weaker pull of Earth's gravity at their altitude and their speed relative to the surface. Without relativity, the system would drift and fail. Near a black hole, this everyday quirk of physics becomes an overwhelming transformation, bending time so profoundly that past and future blur at its edge. To linger near the horizon is to be drawn into paradox. If you could hover safely just outside, your seconds would stretch longer compared to those on Earth. A single hour spent circling close to the abyss might equal years in the wider universe. Stories of interstellar travel sometimes imagine this as a way of leaping through time. Wait by a black hole, and when you return, centuries will have passed. It is not fiction but physics. The closer you come to the horizon, the more extreme the difference becomes, until the gulf is nearly infinite. And yet, for all the strangeness, there is a kind of quiet poetry in it. The black hole does not simply consume matter, it reshapes the very fabric of time around it, stretching moments into forever, erasing events by pulling their light beyond reach. To fall toward one is not only to travel through space, but to drift into a different rhythm of time, one that slows against the background of the cosmos. What relativity teaches us here is profound. Time is not universal. It is not the same for everyone, everywhere. It bends under gravity. It stretches under speed. It changes depending on where you are. And in the presence of a black hole, it reaches its most dramatic expression. To stand far away is to see the fall as eternal. To fall inward is to feel it pass in an instant. Both truths exist together, side by side, reflections of the same reality, seen from different vantage points. Near the edge of a black hole, the ordinary rules of experience unravel. Light fades, clocks slow, moments stretch until they vanish. It is here that relativity is no longer a set of equations on paper but a living reality, shaping what can be seen and what can never return. Time itself becomes a horizon, and beyond it lies silence. Jets erupt from the darkness in defiance of expectation. A black hole, the very image of gravity's silence, seems as though it should only swallow, only consume, only hide. And yet, in some of the most extraordinary displays the universe offers, black holes announce themselves with colossal streams of energy, blasting outward in opposite directions at nearly the speed of light. These are relativistic jets, born in the chaos of accretion, cutting across galaxies, visible across millions of light years. They are not gentle flickers of light, but cosmic lighthouses so powerful that they outshine entire galaxies, carrying the imprint of the black hole's hunger into the vastness of intergalactic space. The process begins with the accretion disk, that whirling storm of gas and dust spiraling toward the event horizon. As matter is heated to extraordinary temperatures, magnetic fields twist and tangle within the plasma, winding tighter as they are dragged by the spinning disk. These fields can funnel particles outward instead of inward, launching them along the poles of the black hole. In this way, the same system that pulls matter in with relentless gravity also propels some of it outward in defiance, not swallowed, but transformed into a jet. The paradox is striking. A structure defined by consumption, producing streams of creation, visible across unimaginable distances. The speed of these jets is staggering. The matter within them moves at relativistic velocities, meaning close to the speed of light itself. At such speeds, time for the particles slows compared to the rest of the universe, and their energy becomes amplified. When we detect them, the radiation they emit stretches across the spectrum, from radio waves to X-rays and even gamma rays. Some jets are so bright that they can be seen in radio telescopes long after their source galaxy is too faint for optical instruments. They carve luminous lines across the void, messages written in radiation, carrying the black hole's presence far beyond its host galaxy. The largest jets extend for millions of light years, dwarfing the galaxies that birthed them. Imagine a stream of energy so vast that, if it emerged from the center of the Milky Way, it would extend well past our neighboring galaxies. These colossal structures are not merely decorative. They shape their environments, heating intergalactic gas, preventing it from cooling into stars, and sculpting the evolution of galaxy clusters. A jet is not just an outflow, it is feedback on a cosmic scale, a force that regulates how galaxies grow and change over billions of years. Astronomers have captured images of these jets through radio astronomy, revealing shapes that stretch far into the darkness like arms of light. In some cases, when a jet happens to point almost directly toward Earth, we observe what is called a blazar, an object so blindingly bright that it dominates the sky in high-energy emissions. Blazars remind us that the orientation of these cosmic engines matters, and that our perspective can transform them from distant streaks into blazing torches. The mystery, however, is not solved by observation alone. We still do not fully understand how black holes generate such powerful jets. The prevailing theories point to the rotation of the black hole itself, where the twisting of space-time drags magnetic fields into alignment and powers the acceleration of particles. In this view, the black hole's spin is not just a silent property but an active driver, feeding the jet with rotational energy. If true, this means black holes are not only eating matter but converting their very spin into beams of light. The idea that rotation itself can be drained to power, streams millions of light years long, is one of the most astonishing predictions of modern physics. Jets also serve as cosmic probes. Because they extend so far, they illuminate the otherwise invisible structures between galaxies. As they pass through intergalactic gas, they reveal its density, its magnetic fields, its hidden currents. By studying the shape and spread of jets, astronomers can read the conditions of the universe on scales too large to measure directly. Each jet becomes both a signature of its black hole and a tool for understanding the cosmic web that binds galaxies together. Despite their violence, there is something profoundly beautiful about black hole jets. They are order born from chaos, narrow streams of light emerging from the most turbulent regions of the universe. They remind us that even in the act of devouring, the universe creates. Matter that might otherwise vanish without trace is instead transformed into brilliance, carried across time and space as a visible marker of the unseen. From the silence of the horizon emerges not only darkness, but light. Black hole jets are proof that even in the most extreme corners of reality, where gravity rules and time falters, the universe still finds a way to shine. They are the paradoxical song of the abyss, played in beams of near light, reaching farther than imagination, visible long after their source has gone quiet. When two black holes approach each other, the universe holds its breath. These are not gentle encounters, but cosmic collisions, events shaped by billions of years of motion and gravity, when two immense wells of space-time are finally drawn together into one. Each black hole has its own mass, its own spin, its own history of swallowing stars and gas. When they meet, all of that is brought into a final, spiraling embrace. What follows is one of the most violent yet silent events imaginable, a merger that shakes the very fabric of space-time. The dance begins long before the final collision. As galaxies drift through the cosmos, gravity pulls them together, and when galaxies merge, their central black holes are fated to find each other as well. At first they orbit distantly, circling in vast loops that may last millions of years. With time, they draw closer, as friction with gas and stars robs them of energy, shrinking their orbit. This stage is slow, almost stately, a cosmic waltz carried out on scales too large for human intuition. But as the separation narrows, the pace quickens. Their orbits tighten, their speeds rise. The rhythm of the dance accelerates until the two black holes are circling each other at nearly the speed of light. At that point, they begin to stir the universe itself. General relativity predicts that massive objects in motion do not simply bend space-time. They send ripples through it. Gravitational waves. These waves carry energy away from the orbiting pair, and as they radiate outward, the black holes spiral faster still. Each ripple is a whisper of their impending union, a message carried across billions of light years. For most of cosmic history, such waves would have gone unnoticed, their passage through space leaving no mark we could detect. But in 2015, instruments on Earth finally heard them for the first time. Detectors in Louisiana and Washington picked up a faint, rising chirp, the signature of two black holes merging over 1 billion light-years away. Humanity had, for the first time, listened to the universe's deepest rhythm. The final moments of the merger are almost inconceivable. Two horizons draw closer, their distortions of space-time twisting together. In the last fractions of a second, the black holes collide, their masses combining into a single, larger horizon. Energy is released in gravitational waves greater than the output of all the stars in the observable universe combined. Yet it is not light or heat but a vibration of space-time itself, a ripple expanding outward at the speed of light. The new black hole settles into stability, its ringing fading like the aftershock of a struck bell. What remains is larger, heavier, and perfectly silent once more. For astronomers, these mergers are more than spectacles. They are laboratories of gravity. By studying the precise shape and timing of gravitational waves, scientists can measure the masses of the black holes, their spins, even test the predictions of relativity in its most extreme domain. Each signal is a fingerprint, unique and unrepeatable, telling the story of a union written in space-time. Hundreds of such events have been detected since that first discovery, each one a glimpse into the hidden lives of black holes scattered across the cosmos. But the significance reaches beyond physics. Black hole mergers also shape the growth of galaxies. Every time two galaxies collide, their central black holes may eventually merge, building the supermassive objects we see today. The giants like Ton 618 or Holmberg 15 amperes were not born whole. They are the product of countless mergers across billions of years, each collision adding mass and energy, each leaving behind a black hole larger than before. Mergers are the engines of growth, one of the ways the universe assembles its titans. There is something both terrifying and beautiful about this process. On one hand, it is violence at the highest possible scale, the collision of invisible monsters that warp space and time itself. On the other, it is an event that gives us a way to see the unseen, to hear the silent, to measure the unmeasurable. Gravitational waves allow us to witness black holes not just as static shadows, but as active participants in the drama of the cosmos, colliding, merging, and reshaping reality. When two black holes collide, we do not see sparks or explosions. We see silence and feel waves, the universe quivering as though in recognition of its own depth. These events remind us that the cosmos is not static but alive, that even in the deep darkness, motion continues, cycles complete, and new structures are born. A merger is not only an ending but a beginning, a moment when two paths become one, and the story of gravity is rewritten in the ripples that spread outward forever. Galaxies look serene when viewed from afar, luminous spirals painted delicately across the dark canvas of the sky. Yet behind this beauty is a delicate balance of forces, and at the heart of that balance lies something that seems, at first, out of place. A black hole. These silent centers do not simply lurk as passive anchors of mass. They are engines of regulation, shaping their galaxies in ways that are both subtle and profound. Without them, galaxies might burn too fast, blaze too bright, and die too young. The raw material for stars is gas. Vast clouds of hydrogen and helium drifting through a galaxy. Left unchecked, these clouds collapse under gravity, forming stars in great numbers. But if the collapse happens too quickly, a galaxy can use up its supply of gas in a cosmic instant, flaring briefly with light before fading into darkness. Galaxies need a regulator, something to slow the pace of star birth, to stretch their resources across billions of years. This is where black holes play their paradoxical role. By feeding on matter, they release enormous amounts of energy, and that energy pushes back on the galaxy itself. When a supermassive black hole consumes gas and dust through its accretion disk, the process is astonishingly inefficient in terms of feeding, yet dazzlingly efficient in terms of radiation. A fraction of the matter is swallowed, but a much larger portion is converted into light and energy, heating the surrounding gas. This energy output, sometimes exceeding that of every star in the galaxy combined, can prevent new gas clouds from cooling enough to collapse into stars. It is as though the black hole, in devouring matter, exhales heat and radiation that spread through its environment, keeping the galaxy from exhausting itself too soon. Jets are part of this regulation as well. When they stream outward from the poles of black holes, they do more than announce the presence of the abyss. They plow through interstellar and intergalactic space, stirring gas and scattering it. The jets heat entire regions of a galaxy's halo, disrupting the calm necessary for star formation. While this may sound destructive, it is in fact essential. Without this feedback, some galaxies might collapse into runaway bursts of star creation, burning their fuel in a frenzy and leaving nothing for the long arc of cosmic history. The black hole's violence becomes a kind of patience, forcing the galaxy into a slower rhythm. Astronomers have seen this process at work in massive elliptical galaxies, where central black holes regulate their hosts so thoroughly that only a trickle of new stars form. The jets inflate bubbles in the surrounding hot gas, cavities visible in X-ray observations, proof that the black hole has injected energy into its environment. In clusters of galaxies, the central black holes become guardians of balance, keeping the immense gas reservoirs from cooling too quickly. Even the brightest cluster galaxies, swollen with stars, owe their survival to the quiet hand of their black holes, which prevent them from consuming all their fuel in one bright flash. In spiral galaxies like the Milky Way, the process is gentler, but no less important. Sagittarius A times is quiet now, but evidence suggests it was more active in the past, sending out flares and perhaps even small jets that helped regulate the star-forming regions around the galactic center. The Milky Way has sustained star birth for billions of years, neither collapsing into quiescence nor burning itself out, a testament to the balance maintained at its core. We are, in a sense, the beneficiaries of this regulation. Without it, our galaxy may have consumed its fuel too quickly for stars like the Sun to form and for life to emerge on a small blue planet orbiting one of them. It is strange to think that what seems like destruction is, in fact, creation's ally. The energy unleashed by black holes ensures that galaxies live long lives. By heating, scattering, and regulating gas, they stretch out the era of star formation, giving rise to stable planetary systems and the slow unfolding of complexity. Black holes are not merely the end of things. They are caretakers of time, extending the lifespan of galaxies far beyond what would otherwise be possible. This role transforms the way we see them. They are not only the monsters at the centers of galaxies, swallowing light and matter. They are also gardeners of the cosmos, pruning, regulating, and ensuring that the galactic ecosystem does not collapse under its own abundance. In their silence and in their fury, they create the conditions for longevity. Galaxies shine because their black holes hold them back from burning too fast. So when you look at the band of the Milky Way stretched across the night sky, know that its beauty exists in part because of the unseen core at its center. The spiral arms, the billions of stars, the quiet cradle of our own solar system, all of it has been shaped by the push and pull of a black hole we will never see directly. In the heart of darkness lies the key to balance, and in that balance, the possibility of light that lasts. High above and below the plane of the Milky Way, two ghostly structures rise like balloons of light, stretching for tens of thousands of light years into space. They are known as the Fermi bubbles, immense lobes of radiation that glow faintly in gamma rays, invisible to human eyes but clear to our most sensitive detectors. Their sheer size defies imagination. Each bubble spans a region larger than the galaxy itself, like scars etched into the sky. And they are not ancient fossils of the Big Bang, nor the echoes of supernovae. They are evidence of something that happened at the very heart of our galaxy, something violent, something tied to the black hole at its core. Sagittarius A times may appear quiet now, a subdued giant feeding only in small bursts, but the Fermi bubbles tell us that it was once far more active. To create such structures requires energy on a scale only a black hole can provide. Astronomers believe that millions of years ago, Sagittarius A times erupted in a phase of furious accretion, swallowing gas and perhaps even stars, and in the process unleashing winds and jets powerful enough to punch through the galaxy. The result was a release of energy so immense it blasted plasma outward, carving twin cavities above and below the galactic disk. What remains today are the glowing outlines of those outbursts, still bright in gamma rays long after the event itself has ended. The bubbles are not perfectly smooth. Observations reveal ripples and edges, signs of turbulence, as if the gas within them still churns from the force that created them. They rise like smoke from an ancient fire, lingering long after the flames have gone out. To measure them is to measure time itself, to look back millions of years into the history of our galaxy and glimpse a moment when its core was alive with violence. Our quiet black hole was once a quasar, blazing so brightly it may have lit the night sky even from Earth, had we been here to see it. But the Fermi bubbles are not the only echoes of past activity. Radiation signatures across multiple wavelengths point to smaller flares that Sagittarius A times has unleashed more recently. X-ray light reveals streams of energized gas near the galactic center, hints that the black hole has not been entirely silent. Some clouds of gas near the core shine unusually bright, as if reflecting echoes of an outburst that happened only a few hundred years ago. These are cosmic afterimages, like the glow on the horizon after lightning strikes. They tell us that our black hole, though calm by cosmic standards, still flickers with occasional hunger. What makes these echoes remarkable is their scale. The Fermi bubbles themselves are hundreds of thousands of light-years tall, dwarfing our entire galaxy's disk. They are proof that a black hole, though invisible, can leave marks that stretch across intergalactic space. They also remind us that galaxies are not static pictures but dynamic stories, changing over time as their central engines flare and fade. The Milky Way, so peaceful in its spiral arms, bears the scars of its core's tempests. For astronomers, these signatures are not just curiosities. They are tools to reconstruct the life of our galaxy's black hole, to understand when and how it fed, and how those feeding episodes shaped the stars around us. By studying the Fermi bubbles, we can estimate how much energy was released, how long the outburst lasted, and how it influenced the Milky Way's ecosystem. These echoes show us that even a black hole as subdued as Sagittarius A times has the power to alter the entire structure of the galaxy when it awakens. There is something humbling about standing under the night sky and knowing that invisible towers of radiation loom far above, relics of an outburst that happened long before our species existed. They are reminders that what seems eternal and unchanging is, in truth, alive with history. Every galaxy carries echoes like these, whether in bubbles of radiation, jets of gas, or scars carved into intergalactic space. Black holes may spend most of their lives in silence, but when they erupt, the marks linger for millions of years. The Fermi bubbles are our galaxy's memory, the sky itself holding on to the moment when darkness flared with unimaginable power. They are echoes of violence, written in light we cannot see, a testament that even silence has a past, and that the center of our galaxy is not just a place of stillness, but a stage for forces that can shake the heavens. Between the familiar categories of black holes, the stellar mass remnants of collapsed stars, and the supermassive giants anchoring galaxies, there ought to be a middle ground. Astronomers have long suspected that there exists a population of intermediate mass black holes, too large to be born from a single star's death, yet too small to rule over galaxies. These are the smallest giants, elusive and rare, hiding in the shadows between the extremes. To find them is to uncover missing pieces of the black hole story, a bridge between beginnings and endings that has so far remained mostly invisible. The existence of intermediate black holes makes sense on paper. Stellar mass black holes can reach perhaps a few dozen times the mass of the Sun, sometimes stretching to 100 in exceptional cases. Supermassive black holes, by contrast, start in the millions of solar masses and climb from there. But how could such monsters appear if there were no stepping stones in between? Nature rarely builds from nothing. If galaxies hold black holes weighing billions of suns, there should also exist black holes of thousands or tens of thousands of suns, seeds waiting in the middle, clues to how the giants grew. And yet, finding them has been one of astronomy's hardest hunts. Intermediate mass black holes do not blaze like quasars, nor do they announce themselves as strongly as their supermassive cousins. They are too light to dominate galaxies, and too heavy to be born in common stellar deaths. They live in the in-between, subtle and shy. Their gravity is powerful, but not enough to warp whole galaxies. Their feeding may be quiet, producing flares too faint for our instruments to see. They are ghosts within shadows, detectable only when circumstances align in just the right way. Hints have emerged, scattered and fragile. In dense star clusters orbiting galaxies, astronomers have found motions of stars that suggest a heavy but unseen presence at the center. Perhaps a few thousand solar masses, too much for a cluster of stars, too little for a galactic giant. In ultraluminous X-ray sources, strange emissions hint at accretion too strong for a normal stellar black hole, but not bright enough for a supermassive one. And in rare cases, Gravitational waves detected from distant mergers point to black holes in the middle range, colliding and revealing their mass through the ripples they send across space-time. None of these signals alone is proof, but together they form a growing pattern, a suggestion that the missing middle may indeed exist. The search is more than academic. Intermediate mass black holes, if confirmed, would explain how supermassive ones came to be so quickly in the early universe. Rather than starting from the tiny corpses of stars, perhaps the first black holes grew from these heavier seeds, born from the collapse of primordial star clusters or dense gas clouds. From there, they could merge and feed until they became the titans we see today at galactic centers. Without this missing link, the timeline seems impossibly compressed. How could billion solar mass black holes shine as quasars less than 1 billion years after the Big Bang? The answer may lie in these hidden middleweights. There is a poetry to their possible existence. They are the quiet ones, neither as common as stellar remnants, nor as commanding as galactic anchors. If they are real, they represent transition, a stage of becoming, a reminder that even in the cosmos, greatness often comes in steps. To find them is to trace the ancestry of black holes themselves, to understand how the universe built its monsters not in sudden leaps, but through gradual accumulation. Future instruments may finally reveal them with certainty. More sensitive X-ray telescopes could catch their faint flares. More precise gravitational wave detectors might hear their collisions in the silence of space. And as our ability to map the motion of stars grows sharper, we may uncover more clusters where unseen giants of a few thousand solar masses lurk. Each new piece of evidence will bring us closer to answering a question that has lingered for decades. Does the universe truly contain this hidden middle ground? For now, the hunt continues, and the smallest giants remain tantalizing phantoms. They remind us that the cosmos is not always loud in its revelations. Some truths lie in whispers, in the subtle tug of stars, in the faintest flicker of X-rays, in ripples too soft for our ears, until the right instruments amplify them. Whether in clusters, in dwarf galaxies, or drifting through intergalactic space, these possible black holes carry with them the story of how the largest came to be. In their absence, there is still wonder. The very fact that we seek them shows how far our questions have reached, how we are no longer satisfied with the extremes, but yearn to fill in the spaces between. The smallest giants, if they exist, are not just black holes. They are the missing lines in the narrative of cosmic growth, the quiet evidence that even the most incomprehensible things in the universe had beginnings that made sense, steps that led them from the ordinary to the infinite. In the deep past of the universe, when the first galaxies were only beginning to ignite, black holes had already grown into giants. This is one of the great puzzles of cosmology. How could objects so massive have taken shape so quickly, within less than 1 billion years after the Big Bang? The light from those ancient quasars travels across more than 13 billion years to reach us, carrying with it a question about speed, growth, and the strange efficiency of the early cosmos. Quasars are black holes caught in the act of feeding, their accretion disks blazing with more energy than all the stars of their galaxies combined. The brightest quasars from the early universe shine so intensely that we can see them across the cosmic gulf, tiny pinpricks in the darkness that speak of objects weighing billions of suns. Ton 618, the largest known today, is only one in a family of monsters whose ancestry stretches back to that ancient epoch. But while we can observe them, the mechanism by which they reached such enormity in such a short time remains partly hidden. One theory imagines that the seeds of these early black holes were heavier than those formed by collapsing stars today. Instead of starting with black holes of 10 or 20 solar masses, the first seeds may have weighed thousands, born from the direct collapse of dense primordial gas clouds. In the chaotic young universe, gas was abundant and unpolluted by heavy elements, allowing it to collapse quickly and efficiently. These direct collapse black holes would have given the early cosmos a head start, providing the foundation upon which billion solar mass quasars could grow in just a few 100 million years. Another possibility lies in relentless growth. The early universe was rich with material, galaxies colliding and merging far more frequently than they do now. A black hole could have grown rapidly simply by consuming the torrents of gas flowing toward galactic centers, or by merging with other black holes spawned in nearby regions. If conditions were right, accretion could proceed at or even beyond the limits we see today, supercharging their growth in ways that are difficult to replicate in the modern, calmer universe. What we see as impossibly fast may have been natural in that era of chaos. Gravitational waves have added new pieces to the puzzle. By catching the ripples from colliding black holes, astronomers can infer the masses of the participants, some of which appear larger than expected for ordinary stellar remnants. These may be signs of hierarchical growth, where one generation of black holes merge to form another, stepping stones toward the supermassive titans of the early quasars. Each merger sent out waves that we only now detect, faint signals of ancient unions that fed the growth of giants. There is also the role of dark matter to consider. The invisible scaffolding of the universe shaped the formation of galaxies, pulling gas into dense halos where stars and black holes could form. Perhaps dark matter's gravitational wells created the perfect nurseries for rapid black hole growth, concentrating matter into pockets where seeds could grow without restraint. If true, then the quasars we see today are not only black holes but also monuments to the architecture of dark matter itself. To observe these ancient quasars is to look back almost to the dawn of time. Their light has crossed nearly the entire history of the universe to reach us, carrying not only answers but mysteries. We see them as they were when the universe was less than a tenth its current age, already vast, already bright, already dominating their galaxies. The paradox is not that they exist, but that they exist so soon. How could gravity and matter have conspired to create them in such haste? The search for answers continues, with telescopes that peer deeper and sharper into the past. The James Webb Space Telescope has already begun to reveal galaxies from the first few 100 million years after the Big Bang, some with evidence of black holes lurking at their centers. Future instruments will refine this picture, tracing the growth of the earliest giants and testing theories of direct collapse, rapid accretion, and mergers. Each discovery is a step toward understanding how the universe's darkest objects could also be its first beacons. There is something almost mythic about these early black holes. They are like ancient kings, enthroned before the kingdoms around them had even formed, ruling over galaxies still in their infancy. Their light comes to us as an echo of a time when stars were new and space was still raw with creation. And though they seem impossibly far away, their story is tied to ours. For without them, galaxies like the Milky Way might not have taken shape as they did. The first quasars shaped the scaffolding of the cosmos, and in that shaping, they set the stage for everything that followed. In their brilliance, we see both mystery and inevitability. The inevitability of gravity, drawing matter together, and the mystery of how it did so with such urgency in the youth of the universe. They are proof that even in the beginning, darkness was already present, already powerful, and already capable of turning silence into light. At the frontier of black hole science lies a territory where our understanding begins to fray, where the equations of general relativity and the laws of quantum mechanics clash like rival rulers over the same kingdom. Each governs reality with unmatched precision in its own realm. Relativity for the cosmic, quantum theory for the subatomic. But inside a black hole, where gravity compresses matter to unimaginable densities, the two sets of laws must coexist. And there, on that edge of knowledge, they do not agree. At the heart of the paradox is the singularity, the place where space and time collapse into a point of infinite density. General relativity predicts it, yet infinities in physics are usually signs of something missing in the theory, a failure rather than a truth. If matter is squeezed to scales smaller than atoms, quantum mechanics should take over, yet relativity insists on its own authority. In this tug-of-war, neither framework yields, and the result is a mystery no one has yet solved. To truly know what happens at the core of a black hole, science needs a theory of quantum gravity, a single language that unites the vast and the tiny. Hints of such a theory come in thought experiments and in the strange predictions of Stephen Hawking. In the 1970 seconds, he showed that black holes are not perfectly black. Through the lens of quantum mechanics, the vacuum of space is alive with fleeting particle-antiparticle pairs. Near a horizon, one particle may fall in while the other escapes, carrying away a tiny amount of the black hole's energy. Over vast spans of time, this process, Hawking radiation, would cause black holes to lose mass, to shrink, and eventually to evaporate. What was once considered eternal is revealed to be mortal, though on timescales so immense they make the age of the universe seem brief. This discovery opened another riddle. If black holes evaporate, what happens to the information about the matter they once consumed? In classical physics, information cannot be destroyed. It may transform, but it persists in some form. Yet Hawking radiation appears to carry no record of what fell in, only random energy. If true, this would mean information is erased from the universe, an idea at odds with quantum mechanics. This information paradox has haunted physics ever since, a wound in the fabric of theory, suggesting that something vital remains undiscovered. Various proposals have been made. Some suggest that information is encoded in subtle correlations within the radiation itself, invisible at first glance but present nonetheless. Others argue it might be stored on the event horizon, like a hologram, leading to the radical idea that the three-dimensional world we experience is itself a projection of information painted on the universe's surface. This is the holographic principle, a concept both staggering and unsettling, one that recasts reality as something stranger than we perceive. And yet, despite decades of debate, no definitive solution has emerged. String theory, loop quantum gravity, and other candidates for the ultimate theory all attempt to weave space-time and quantum mechanics into one cloth, but the black hole remains the harshest proving ground. To explain what happens beyond the horizon is to touch the deepest truths of the universe, to understand not just black holes, but the very nature of space, time, and reality itself. The beauty of this mystery is that it cannot be answered with speculation alone. Observations, too, are beginning to press on these boundaries. Gravitational wave detectors, imaging arrays like the Event Horizon Telescope, and next-generation observatories will push us closer to seeing the effects of quantum and relativity together. Though we may never peer into the singularity itself, we can glimpse the clues it leaves at the horizon, in the behavior of light, in the patterns of waves, in the faint whispers of radiation. The edge of knowledge is not a wall but a horizon, much like the one around a black hole. We approach it slowly, gathering fragments, testing ideas, knowing that beyond it lies something more complete than we yet imagine. Whether that truth comes in the form of a new theory, a unification of the great frameworks, or a radical rethinking of reality itself, the black hole will remain both the problem and the guide. It is fitting that the darkest objects in the universe illuminate its greatest mysteries. They are laboratories of extremes, places where physics as we know it breaks, demanding new visions. To follow them is to walk to the frontier of human understanding, where certainty falters and wonder takes over. And in that wonder lies the possibility that the universe is stranger, richer, and more profound than even our most daring theories suggest. From the beginning of human storytelling, the idea of a consuming darkness has haunted imagination. Long before the word black hole was ever coined, cultures told tales of monsters that swallowed light, of abysses that devoured worlds, of gates into realms unseen. In Norse mythology, the great wolf Fenrir threatens to consume the sun at the end of time. In Hindu cosmology, the dance of Shiva destroys and remakes the universe in cycles of creation and collapse. Across traditions, the motif of an all-devouring force appears, reflecting both fear and reverence for powers too vast to comprehend. When science finally revealed black holes, they seemed less like discoveries and more like the realization of myths that humanity had always carried. The metaphor of the black hole slipped easily into language. Even before the first astronomical evidence was secure, the term evoked something final and inescapable. People began to use it to describe debt, grief, addiction, or anything that seemed to pull endlessly inward. To call something a black hole was to name it as a force that consumes without return, a place where energy and effort vanish without trace. The scientific object and the human metaphor grew together, each amplifying the other. In literature, black holes often serve as symbols of the unknown, of fear, or of transcendence. Writers imagined them as prisons, gateways, or both at once. Science fiction seized on them as plot devices, portals to other universes, weapons of unimaginable power, traps for careless travelers. Arthur C. Clarke and Isaac Asimov wrote of them with awe and caution, blending real physics with speculative wonder. To step near a black hole became shorthand for facing the ultimate limit, the edge of what can be known. Cinema amplified their hold on the popular mind. In the 1979 film The Black Hole, Disney envisioned them as both menace and mystery, mixing horror with cosmic spectacle. More recently, Interstellar offered a vision shaped by actual physics, rendering the accretion disk around a rotating black hole with breathtaking realism. Audiences were captivated not just by the image, but by the ideas. Time dilation, horizons, the possibility of survival beyond the collapse. The black hole was not merely an effect on screen, but a character in its own right, shaping the destiny of the story. In such films, science is not diminished but exalted, made into a stage for human emotion and imagination. Even in music and art, the black hole appears as inspiration. Bands name albums after them. Painters render spirals of light and shadow. The image of a dark center pulling all into silence resonates with the struggles and yearnings of the human condition. To gaze at a painting of a swirling void, or hear lyrics invoking an endless pull, is to feel that cosmic metaphor folded back into personal experience. Black holes are at once scientific objects and mirrors of inner life. Part of their power lies in their duality. They are terrifying because they represent annihilation, the loss of self, the collapse of order. But they are also beautiful because they reveal the strange and subtle workings of the universe, where gravity bends light and time stretches toward eternity. They remind us that destruction and creation are not opposites, but partners, that the same forces which erase stars also shape galaxies. Culture reflects this paradox, seeing in black holes both death and possibility, doom and transcendence. For scientists, the challenge has been to balance fact with imagination. Real black holes do not serve as shortcuts to distant galaxies, nor as cosmic drains swallowing everything in sight. And yet, the metaphors they inspire are not wrong. They express the sense of awe that science itself cannot escape, the awareness that in these objects we are confronting something that strains against the limits of language. The cultural weight of black holes makes them more than astrophysical phenomena. They have become symbols of the unknown, anchors for imagination across science and art alike. In the end, what unites myth, metaphor, and science is wonder. The black hole is not just a feature of the cosmos, but a canvas on which humanity projects its deepest questions. What it means to face endings, what it means to lose or to transform, and what it means to stare into mystery. Whether in ancient tales of world-devouring beasts, in the equations of Einstein, or in the flickering images on a cinema screen, the theme is the same. Darkness at the center, light spiraling around it, and the question of what lies beyond. We fear black holes, and we need them. They haunt our imagination because they embody both the terror of loss and the beauty of mystery. In them, The universe whispers back the stories we have always told, of devouring darkness, of hidden doors, of the thin line between destruction and creation. Far above the quiet spirals of the Milky Way, another galaxy approaches, silent but inevitable. Andromeda, our nearest large neighbor, is on a collision course with us. It is not rushing in with sudden violence, but drifting closer in a slow, majestic glide, pulled by the invisible hand of gravity. Over the course of billions of years, the space between will shrink until the two galaxies entwine, their stars crossing paths like dancers in a crowded hall. To witness such a future is to imagine a night sky transformed, its familiar constellations replaced by arcs of light as Andromeda swells, fills the heavens, and finally merges with our own. At first, the galaxies will not so much collide as pass through one another. Though each holds hundreds of billions of stars, the distance between stars is so vast that few will actually collide. Instead, gravity will pull them into new orbits, reshaping the structure of both galaxies. Spirals will distort into streams, stars will be flung outward into tidal tails, and clouds of gas will compress to ignite new waves of star formation. To an observer far in the future, the sky will look alive with motion, as if two vast whirlpools of light had been stirred into one. At the centers of both galaxies lie black holes, Sagittarius A times in the Milky Way, and a larger one within Andromeda. When the galaxies merge, these two giants will begin a long approach toward one another. At first, they will circle distantly, shepherding stars with their combined pull. Over millions of years, dynamical friction will drain their momentum, bringing them closer, until, eventually, they spiral together. Their merger will release gravitational waves that ripple across the cosmos, a silent broadcast of our galaxy's transformation. The final product will be a single, far larger black hole, carrying the mass and memory of both ancestors. For the stars around them, this union will mean new orbits, some drawn closer to the heart, others cast into the galactic outskirts. Yet for the Sun and its planets, if they still exist by then, the collision will not be an immediate catastrophe. It is more likely we will be carried into a new orbit, our night skies dramatically altered, but our solar system intact. From Earth's perspective, the danger is not stellar collisions, but the slow changes to the galaxy's structure, the gradual reshaping of its rhythms. The Milky Way and Andromeda are destined to form what astronomers call an elliptical galaxy, a smoother, rounder structure lacking the graceful spirals we know today. The new galaxy has already been given a name, Milkomeda. In its vastness will be the combined heritage of both, their stars mingled, their black holes merged, their histories inseparably joined. It will be a galaxy brighter and more massive than either alone, a monument to the quiet inevitability of gravity. Sagittarius A times will not vanish in this process. Instead, it will evolve, joining with Andromeda's central black hole to become something greater. From its quiet state today, feeding only occasionally, it may ignite again in the turbulence of merger, accreting streams of gas and flaring with new energy. For a time, the heart of the new galaxy may shine as a quasar, visible across the universe, announcing the birth of Milkomeda in light and radiation. What is silent now may roar once more in the far future. All of this will unfold on timescales beyond human experience. 4 billion years until the galaxies touch, another billion until the merger completes, eons before the black holes unite. Yet to imagine it is to step outside the boundaries of human time and glimpse the destiny of our home. The constellations that guided ancient navigators, the patterns poets once traced, the familiar arc of the Milky Way, these will all fade into a different sky. In their place will rise new rivers of starlight, the legacy of two galaxies entwined. Our fate with Andromeda is not catastrophe but transformation. The stars will not burn out in sudden chaos but continue to shine in new arrangements under the guardianship of a greater black hole at the center. The future of Sagittarius A times is not silence but union, and through that union, rebirth. The galaxy we call home is not fixed, not eternal, but part of a larger story still unfolding. And in that story, even the most immense structures we know are destined to change, to merge, to become something new beneath the endless pull of gravity. Across the dark, wide sky, Andromeda moves toward us in silence. To the naked eye, it appears as a faint smudge of light, a delicate spiral hovering at the edge of perception, so far away that its vastness collapses into a blur. Yet the reality is that this faint glow is a galaxy of 1 trillion stars, a neighbor whose slow drift conceals its destiny. In 4 billion years, it will no longer be a distant haze. It will touch us, not suddenly, not explosively, but with a steady inevitability, a cosmic waltz that draws us together step by step. The Milky Way and Andromeda are already bound by gravity. They circle each other now, not yet locked in embrace, but already committed to one. For billions of years, the galaxies will approach, the gap shrinking by hundreds of thousands of kilometers every hour. To us, it is imperceptible, but across the expanse of time, the motion is relentless. At first, the change will be subtle. Andromeda will appear larger in the night sky, its faint disk no longer a blur, but a structure visible to the eye, with spiral arms stretching like faint brushstrokes across the dark. Then, as millions of years pass, it will grow brighter, more detailed, dominating the sky until it dwarfs the familiar constellations. There will come a time when Earth's night will be painted with the arcs of another galaxy, not as a distant smudge, but as an immense companion glowing across the heavens. When galaxies draw close, their gravity does not pull them together like solid bodies colliding. Instead, tidal forces spread across them, uneven pulls that tug on their stars and gas. Just as the moon raises tides on Earth's oceans, Andromeda will raise tides in the Milky Way, and the Milky Way in Andromeda. Stars will not crash headlong into one another. The distances between them are too great. But their paths will twist. Some will be flung outward into long streams that trail into intergalactic space, while others will be pulled inward, drawn closer to the merging cores. These tidal tails, arcs of stars stretching tens of thousands of light years, will be the signature of the dance. Ribbons of light that mark the slow unraveling of each galaxy's spiral shape. As the galaxies pass through one another, gas clouds will collide even if stars do not. Vast reservoirs of hydrogen, usually drifting quietly, will be compressed by the meeting of galaxies. This compression will spark new rounds of star formation, as if the collision had struck flint against steel and thrown sparks into the dark. For a time, both galaxies will blaze with new light, their spirals dotted with clusters of newborn stars, blue and hot, burning their lives in mere millions of years. These bursts of creation will be the fiery consequence of the encounter. Galaxies that might otherwise have been fading rekindled into brief brilliance. From the perspective of a world orbiting a quiet star in the Milky Way, the night sky will transform into a shifting panorama. First, Andromeda's disk will loom, luminous and immense. Then, as the galaxies interpenetrate, streams of stars will cut across the heavens like glowing rivers. The familiar constellations, shaped by the stars of our own galaxy, will be drowned beneath these new patterns. Eventually, the sky will be filled not with isolated pinpricks of light, but with luminous arcs, the outlines of two galaxies caught in embrace, as if the heavens themselves had bent down to paint their story across the earth. The word collision suggests destruction, the shattering of stars and the violent smashing of worlds. But this is misleading. Space is too wide, the stars too small compared to the gulf between them. The overwhelming majority will pass untouched, their planetary systems continuing their orbits unaware of the vast drama unfolding. What changes are the paths of galaxies themselves, their structures distorted, their shapes stretched and reshaped by gravity. Collision in this sense is more like a slow sculpting, the careful reshaping of spirals into new forms, the dissolution of arms into halos, the birth of something greater than either galaxy alone. And yet, for some, the dance will mean exile. As orbits shift, some stars will be thrown outward, cast into the emptiness between galaxies. These intergalactic wanderers will no longer belong to any one home, drifting alone across the cosmic void. Others will be drawn deeper inward, circling ever closer to the cores, perhaps feeding the black holes that wait at the center. Still others may find themselves trapped in the tidal streams that arc across space, carried into ribbons of light stretching between the merging galaxies. Each star's fate will be written not by direct impact, but by the vast, slow mathematics of gravity. The Milky Way and Andromeda are not alone in this. The smaller Triangulum galaxy hovers nearby, a modest spiral compared to its giant companions. It may be drawn into the merger as well, captured and consumed in the process. This is the way of the cosmos. Galaxies do not remain separate forever. They interact, they merge, they consume smaller companions, they grow. The process is called galactic cannibalism, not because it is cruel, but because it is inevitable. The Milky Way itself has already eaten smaller galaxies, their stars now blended into our halo. Andromeda has done the same. The merger of our two great spirals is only the next step in a long tradition, a reminder that growth in the universe often comes through union and transformation. For billions of years, this slow dance will unfold. First the approach, then the first pass, the long tidal tails stretching into space, the bursts of star formation lighting both galaxies anew. Then another pass, closer this time, their cores circling one another in a tightening spiral. Finally, the long settling, as stars redistribute into new orbits, spirals give way to an elliptical form, and the black holes at the centers merge. It will not be quick. The process of becoming one will take longer than the entire span of human history, multiplied many times over. But in the end, the Milky Way and Andromeda will no longer exist as separate galaxies. They will have given birth to something new, a single massive elliptical galaxy glowing in the cosmic night. The slow dance of collision is not destruction, but transformation. It is a reminder that in the cosmos, change is the only constant. Even galaxies, with their billions of stars and their ages stretching across eons, are not permanent. They grow, they merge, they evolve. And we, living in the quiet span of a single moment, are part of that story. Our night sky holds not just the patterns of the present, but the promise of what will come. To look at Andromeda's faint smudge is to see the future approaching, to glimpse the dance already begun. When the Milky Way and Andromeda have finally completed their long embrace, what emerges will not resemble the galaxies we know today. The delicate spiral arms of each, so graceful and distinct, will have been unraveled by tidal forces, smeared into luminous streams before being gathered into a new whole. Over time, the swirls will fade, the patterns dissolve, until all that remains is a vast elliptical shape, rounder, smoother, less adorned. The astronomers of the distant future, if any remain, will look upon the sky and see not the winding arms of a spiral, but a single, swollen spheroid filled with the blended light of two galaxies. That galaxy already has a name waiting for its birth, Milkomeda. The reign of this new galaxy will begin with chaos. As the Milky Way and Andromeda interpenetrate, stars will be tugged into new orbits, clusters stretched into streams, and gas clouds shocked into collapse. The turbulence will ignite bursts of star formation, galaxies that once glowed with steady light, suddenly flickering with newborn blue stars burning furiously. For hundreds of millions of years, Milkomeda will sparkle with these clusters, each one a brief flare of brilliance against the backdrop of galactic transformation. But like sparks thrown from a fire, they will burn out quickly, their fuel exhausted, leaving behind remnants, neutron stars, black holes, and quiet white dwarfs cooling in the dark. As the merger settles, the fuel for such creation will dwindle. The reservoirs of hydrogen that once flowed so freely will have been consumed or blown outward by the violence of starburst and black hole feeding. Milky will age quickly into a quieter phase, its bursts of life giving way to long-term quiescence. Red stars, faint but enduring, will dominate its population. The galaxy's youth will be written in scattered pockets of blue stars, but its maturity will be defined by the steady glow of countless red dwarfs that will burn for trillions of years, long after brighter stars have vanished. The fate of planetary systems during this reign is varied, written in the subtle pull of gravity and the chaos of chance. Some solar systems will be ejected entirely, flung into intergalactic space by the gravitational slingshot of merging orbits. These wandering worlds, severed from their galaxy, will drift in the cosmic dark, stars with no city, planets with no sky. Others will be drawn inward, pulled toward the center, where the combined black hole waits. There, orbits will become precarious, and some systems may be consumed altogether. Yet most planets and stars, despite the violence of the merger, will survive. The immensity of space ensures that direct collisions remain rare, and though orbits will be altered, many systems will continue their quiet revolutions, largely unaware of the galactic upheaval around them. Invisible to the eye but essential to the shape of Milky is the vast halo of dark matter that surrounds both galaxies. It is this unseen structure that has guided their approach, pulling them together across billions of years. When the galaxies finally fuse, their dark matter halos will merge as well, enveloping Milky in an even larger, more massive cocoon of gravity. This halo will determine the orbits of stars at the galaxy's edge, hold together its scattered remnants, and ensure that the new galaxy remains bound. Without it, the luminous matter we see would be insufficient to create the structure that emerges. Dark matter is the silent architect of Milky, the skeleton upon which its reign is built. What might feel catastrophic when imagined from within is, on cosmic scales, entirely natural. Galaxies are not static things. They grow by merging. They transform by colliding. The Milky Way has already consumed smaller galaxies, their stars now indistinguishable from our own. Andromeda has done the same. The union of two great spirals into a giant elliptical is not an exception but a continuation of this process, one that has been shaping the universe since its earliest days. To witness it is to see cosmic evolution at work, galaxies becoming what they were always meant to be through the slow arithmetic of gravity. And Milky itself will not be alone. Beyond its glowing stars lies the local group, a collection of smaller galaxies, Triangulum, the Magellanic Clouds, and dozens more, that will eventually be drawn into the orbit of the giant. Over billions of years, the local group will consolidate into a single, massive structure, one galaxy swallowing another until only Milky remains. The great web of galaxies that now surrounds us will slowly thin as dark energy accelerates the expansion of space, driving more distant galaxies beyond our horizon. The reign of Milky will be both vast and lonely, a kingdom unto itself, surrounded by emptiness. Still, within that loneliness lies a strange kind of permanence. Stars will continue to shine, though more faintly, as the eons pass. Planets will orbit, some under skies unrecognizable to us, filled with strange constellations shaped by the merger. Black holes will grow in silence, swallowing what drifts too close, anchoring the galaxy as they always have. And the memory of the Milky Way, of Andromeda, will be written in the patterns of orbits, in the faint streams of stars stretched across the halo, in the invisible skeleton of dark matter that holds it all. Milky will be the heir of two galaxies, but it will also be the seed of the future. Its reign is not a conclusion but a chapter in a longer story, the story of cosmic evolution that began with the first structures forming in the early universe. From the collapse of gas clouds to the birth of stars, from the growth of black holes to the merging of galaxies, the universe has always been in motion, always becoming something new. The reign of Milky is only the next step in that endless unfolding, And somewhere within it, perhaps, will still be the traces of us. Not our cities, not our words, not even our species, but the atoms of our bodies, scattered into stars, planets, and dust. We too will be part of Milky's reign, part of the long memory of the universe. The galaxy will not know us, but it will carry us, as it carries everything that has ever been born in the cosmic dance of gravity and light. To imagine Milky is not to imagine an ending, but to glimpse the continuity of existence. The spirals will fade, the shapes will change, but the stars will remain. What we call collision is only transformation, and what we call the end of the Milky Way is only the birth of something greater. In the stillness of the night sky, the faint blur of Andromeda reminds us of that future, a future where galaxies merge and reign together beneath the endless expansion of space. Long after the spirals have faded and the memory of collision has softened into stability, Milky will endure as a single vast galaxy, round and swollen, glowing faintly against the deep black of space. The bright chaos of merger will have passed, the starbursts exhausted, the gas long since consumed or cast outward. What remains will be a quieter realm, a galaxy entering old age. Billions of years from now, the last great wave of star formation will have ceased, and the galaxy will be populated mostly by the elderly. Dim red dwarfs, cooling white dwarfs, neutron stars, and black holes. The reign of Milky will give way to a gentler twilight, one defined not by the birth of stars but by their long, patient decline. At the center of this quiet giant will sit the black hole, the one born from the union of Sagittarius A times and Andromeda's central colossus. Fed by the storms of gas and stars driven inward during the merger, it will have grown to a size far beyond its current millions of solar masses, perhaps tens of millions or more. Around it, stars will continue to circle, pulled by its relentless gravity, the anchor at the heart of Milky. For a time, in the galaxy's middle age, it may have shone like a quasar, its feeding bright enough to light the universe. But in this later era, with little fuel left to consume, it will grow silent again, a dark monarch seated in the core, shaping orbits but offering no light of its own. The stars that remain will be different from the stars we know now. Most of the massive ones will have long since burned themselves out, exploding as supernovae and leaving behind only remnants. Blue stars, the brilliant and short-lived, will be gone entirely. The night skies of surviving worlds will be filled instead with the long-lived red dwarfs, faint but steady, each one capable of burning for trillions of years. White dwarfs, the corpses of once sun-like stars, will cool slowly, glowing dimly for eons before fading into blackness. Neutron stars and black holes will linger, scattered through the galaxy like fossils, the remnants of an era when creation still burned bright. The cosmos will feel older, quieter, with the brilliant diversity of stellar youth replaced by the endurance of stellar age. Planetary systems will still circle their stars, though many will have been altered by the violence of the merger. Some will have been thrown into intergalactic exile, their suns wandering alone in the dark spaces between galaxies. Others will have been pulled into new orbits, flung to the outskirts of Milky, circling far from its luminous heart. A few may have been swallowed entirely, dragged inward, and consumed by the central black hole. Yet countless others will continue much as before, their worlds revolving around their aging stars, bearing skies that look stranger but still familiar in their own way. Life, if it ever found purchase again, might adapt to this dimmer cosmos, or perhaps fade into silence with it. Around Milky stretches the wider universe, but that universe itself will have changed. Dark energy, the mysterious force accelerating cosmic expansion, will continue to push galaxies apart. One by one, galaxies outside our local group will slip beyond the horizon, their light stretched until it can no longer reach us. In the far future, Milky will be alone, an island in the dark, surrounded by nothing but empty space. The great cosmic web, once a vast network of clusters and filaments, will recede until only our own galaxy remains visible. To any astronomers of that age, the universe will appear much smaller, their sky emptied of distant galaxies, their sense of place confined to the single giant they inhabit. Cosmic loneliness will be the legacy of dark energy, a silence imposed by the expansion of space itself. In this silence, the black holes will reign, not just the central one, but the countless stellar mass black holes scattered through the galaxy, each one a remnant of stars long gone. They will outlive nearly everything else, persisting for unimaginable spans of time. Even as the last red dwarfs flicker out and the white dwarfs cool into darkness, the black holes will endure, silent and patient, holding the memory of the stars that fed them. They will be the ultimate survivors, the keepers of the past, long after the last light has faded. It is here, in this far future, that impermanence and endurance meet. The stars we see tonight, vibrant and varied, are temporary. Their lives span millions or billions of years, but they end, each in their own way, leaving remnants behind. Galaxies themselves, vast as they are, transform and dissolve, spirals melting into ellipticals, shapes erased by the passage of time. Yet through it all, something persists. Gravity, black holes, the quiet remnants that refuse to vanish. The universe is not eternal in any one form, but it endures through constant transformation, carrying memory in the very matter and energy that shift from one state to another. And what of us? We are brief flashes of awareness, tiny sparks of consciousness in a cosmos that spans billions of years. Our lives are measured not in eons, but in heartbeats, in breaths, in the fleeting arc of a single generation. Yet even in our brevity, we are part of this story. The atoms of our bodies were forged in stars, scattered by supernovae, gathered into planets, and awakened into thought. When our lives end, those atoms return to the cosmos, continuing the journey that began long before us and will continue long after. We are not separate from the story of galaxies and black holes. We are woven into it. Our existence, one of the ways the universe knows itself. The last light of stars will not come for trillions of years, longer than the span of the universe so far. But it will come. The galaxy will fade, the cosmos will grow dark, and black holes will inherit the silence. And yet, there is beauty in that destiny, not tragedy. For the universe has always been about change, about transformation, about the flow of matter and energy into new forms. The last light will be only another step in that endless process, just as the first light of stars was. The story does not end. It only changes its shape. As we imagine that far future, the loneliness of a single galaxy adrift in the dark, the endurance of black holes in the silence, we circle back to ourselves, to this moment, to this breath, to this awareness. We too are temporary, but we are here, now, alive, in a universe that is vast and changing. The last light of stars may be trillions of years away, but the light of stars is shining on you tonight. And that is enough. You are here, listening, breathing, resting, suspended for a moment in the vastness of thought. And though we've spoken of black holes and galaxies, of the engines of creation and destruction scattered across the universe, the truth is that this story has always been about you. For you are not separate from this cosmos. You are of it. Every atom in your body, every spark of thought in your mind, every breath you take is the consequence of a journey that began billions of years ago in the hearts of stars and the whirling arms of galaxies. The iron in your blood was forged in the collapse of massive stars, scattered across the cosmos by supernovae that once outshone entire galaxies. The calcium in your bones, the carbon that shapes your cells, the oxygen that fills your lungs, none of it could exist without the alchemy of stars that lived and died long before the Earth was born. You are, in the most literal sense, stardust made conscious, matter that once blazed in distant skies, now gathered into the form of a human being capable of wondering at its origins. The The story of black holes is not separate from your own. It is inscribed into your very body. Our galaxy is not just a backdrop for your life, but a structure that cradles it. You live on a small planet circling a modest star, tucked away in one of the Milky Way's spiraling arms. Above you stretches a river of starlight, hundreds of billions of suns orbiting together, all bound to the hidden weight of Sagittarius A times at the center. Every moment of your life, you are moving with that great wheel, drawn in its orbit around a black hole 4 million times the mass of the sun. You may not feel it, but you are in motion, carried endlessly around a silent anchor. Even now, as you rest, your body is spiraling through space at hundreds of kilometers per second, tied to a journey that will last as long as the galaxy itself. Andromeda approaches, a great spiral coming ever closer, destined one day to merge with the Milky Way. The stars of both galaxies will dance together, and their central black holes will meet and combine. If any trace of humanity survives into that far future, our descendants will live beneath skies very different from yours, skies alive with streams of stars and the glow of galactic collision. But even if our species fades, the atoms that now compose you will continue, scattered back into the cosmic ocean, perhaps to take part in the birth of new stars, new planets, new forms of life. The matter of your body will not vanish. It will only change its place in the endless cycle of creation and destruction that is the universe's heartbeat. This is the truth that black holes, for all their darkness, remind us of. Nothing is truly lost. Matter collapses. Light bends, time stretches and shatters, but energy and information remain, reshaped, transformed, carried forward in ways we do not yet fully understand. You are part of that continuity. What feels like an ending is only a change of form. What seems like silence may yet echo in new patterns of existence. The universe is vast, but it is not indifferent. It has given you a place within it, has arranged the improbable chain of events that led to your being here, now, alive and aware. The galaxies spin, the black holes feed, the stars explode, and out of all of that, you emerged. When you breathe, you carry the cosmos into yourself, and when you exhale, you return yourself to it. There is no boundary between you and the universe. You are a continuation of its story. So rest, knowing you are held by forces larger than imagination. The galaxies turn with you inside them. The stars burn with atoms that once belonged to you and will again. The black holes anchor the great spirals that cradle your life. Even as you drift into sleep, your body and your mind are part of a dance that spans billions of years, a rhythm written into the fabric of existence itself. And in this quiet moment, let yourself feel the stillness that lies at the heart of it all, the same stillness that surrounds the black hole's event horizon, the silence at the center of galaxies, the pause between the birth and death of stars. It is a silence you carry too, in your own breath, in your own heart. The cosmos is vast, but tonight it folds close around you, reminding you that you are not apart from it, but of it. Stardust, memory, and light, spiraling in an infinite story. Sleep now, carried on that story, safe in the knowledge that the universe is within you, and you are within it.